I want you to take a second and just look around wherever you are right now.
Yeah, seriously, just stop whatever you're doing for a moment and really look at your surroundings.
Right, like maybe you're noticing the vibrant red of a stop sign outside your window, or the deep blue of a sapphire ring you might be wearing.
Or, perhaps most obviously look at the device you're using to listen to this right now.
Exactly. The glowing screen of your smartphone, or the incredibly complex computer chip doing, billions of calculations a second just so you can hear my voice.
And here's the thing. What if I told you that every single one of those things, the color of the gem, the glow of the screen, the massive computational power of that chip, what if I told you it all relied entirely on the fact that the materials making them up are fundamentally broken?
It's a crazy concept. Because we spend so much of our lives, right, just chasing this idealized concept of perfection.
Oh, absolutely. And certainly so much of our scientific history is built on that. We want the flawless diamond, the pristine, unblemished surface, the perfectly ordered system.
But the reality of the physical world is, well, it's entirely the opposite. The phenomena that make the universe interesting, the things that give it texture and capability, they almost always arise from the flaws.
Right. And that is exactly what our deep dive is about today.
Yes. We are venturing into the often invisible but absolutely essential world of solid-state physics. We are using a text we've been reviewing. It's called The Magic of Imperfection, Designing Crystal Defects, as our guide.
That's a fascinating source.
It really is. And our mission today for you, the listener, is to completely dismantle and then reconstruct your understanding of the word perfection.
Because honestly, in the world of material science, perfect crystals they're actually incredibly boring.
They are. They're the equivalent of a blank canvas with no paint on it, or a perfectly tuned guitar with no one to strum the strings. The potential is there, but nothing is actually happening.
Yeah, and the text points out that material scientists, the people designing the future of technology, the ones building the architecture of the digital age, they don't actually spend their days in laboratories trying to force atoms into a completely flawless, unblemished arrangement.
Which is a huge misconception, I think.
Huge. It's a very common misconception. Instead, they are completely obsessed with what the field calls lattice defects.
Lattice defects. So meaning like the mistakes in the structure.
Exactly. The tiny scratches, the missing pieces, the atom squeezed into the wrong spot within the geometric grid of a crystal.
Right.
And the fundamental truth of material science is basically this. If we only had materials with a 100% perfect atomic structure, every gemstone in the world would look like clear glass.
Wow.
And the semiconductor materials that power every electronic device on Earth would be nothing more than dead, useless rocks.
Okay, wait, I need to stop you there because that is a massive claim. No defects means no color and no computers.
Literally, yes.
I definitely want to build up to the computer chips and the screens, but I think we need to start with something we can all easily visualize. Let's start with light and color.
That makes sense.
And to do that, let's look at something you probably have sitting in your kitchen cabinet right now. Table salt.
Yeah.
Sodium chloride.
Oh, that's a great starting point. Because when you look at a high-quality, pure crystal of table salt, perhaps under a magnifying glass, what are you actually looking at?
Well, it's clear. It's transparent.
Mm-hmm.
Like a tiny little ice cube, basically.
Right. It is fundamentally colorless and transparent to visible light. But the text describes a fascinating laboratory experiment that completely alters that state.
Okay.
If scientists take that clear salt crystal and shoot it with X-rays or heat it up inside a chamber filled with a glowing sodium vapor, the completely clear crystal suddenly turns a vibrant, brilliant yellow. Or sometimes a deep purple.
See, this is where my intuition just hits a wall. Because they haven't painted it, right?
Ew.
They haven't dyed it. They haven't fundamentally changed its chemical formula by, turning it into a different substance entirely. It is still just sodium chloride. It's still just salt.
It's entirely the same base material, yes.
So how does heating it in a specific vapor or blasting it with X-rays just conjure a vibrant color out of thin air?
To understand the mechanism behind that, we really have to zoom way down to the microscopic atomic level of that salt crystal. We have to look at the architecture.
The text uses an analogy here that I actually found really helpful. It asks us to imagine the atoms of the salt crystal as a structured playground jungle gym, like those giant repeating three-dimensional grids of metal bars.
Yeah, a rigid, predictable lattice. So in sodium chloride, you have two types of atoms, or ions technically, because they carry an electrical charge, and they make up the joints of this jungle gym.
Right, the pluses and minuses.
Exactly. You have sodium, which has a positive charge, and chlorine, which has a negative charge. They alternate in all three dimensions, plus, minus, negative. And they hold the entire structure together through electrostatic attraction. The positive pulls on the negative, locking everything into place.
It sounds like a beautifully balanced system. Every positive sodium ion is surrounded by negative chlorine ions on all sides, and vice versa. It's this state of perfect electrical neutrality and structural harmony.
It is. Right up until we introduce an external stressor.
Like the X-rays.
Exactly. The X-rays, or the intense thermal energy from the heating process, they act like a sudden, violent earthquake hitting our microscopic jungle gym.
Okay, so the whole thing is shaking.
Right. And the energy transferred into the system is so intense that it actually causes one single negatively charged chlorine ion to literally vibrate out of its designated spot and escape the crystal structure entirely.
So the energy just physically ejects a piece of the lattice. Like one random chlorine ion just gets knocked off the playground and leaves.
It flees the scene. The thermal vibrations just overcome the electrostatic bonds holding it in place. And what is left behind in that alternating grid of pluses and minuses?
Well, an empty spot, right. A hole in the jungle gym.
Yes. And material scientists have a specific term for this. When an atom goes missing from its proper place in the crystal lattice, we call it a vacancy.
A vacancy.
It is the most basic type of point defect. But the story doesn't end with a simple empty space.
Right, because the chlorine ion ran away, but it didn't take everything with it, did it?
It couldn't. And this is a crucial point about the physics of crystals. Even though the physical mass of the chlorine atom is gone, the crystal as a whole system still demands balance.
It has to stay neutral.
Exactly. It must maintain its macroscopic electrical neutrality. Now, the chlorine ion that escaped was negatively charged. If it just left and took its negative charge with it, the entire salt crystal would suddenly have a net positive charge.
And nature doesn't like that.
Nature strongly resists large accumulations of unbalanced charge like that.
So the crystal wants to stay neutral. So to maintain that electrical balance, the escaping chlorine ion is forced to leave something behind. It leaves behind an electron.
That is the physical reality. It leaves an electron behind to balance the books. Because an electron carries a negative charge, it perfectly balances out the positive charges of the surrounding sodium ions that are still sitting in their proper places.
Okay.
But consider the bizarre nature of this situation. That electron no longer belongs to any specific atomic nucleus. It is just sitting there, trapped all by itself in the empty space in the physical vacancy where the bulky chlorine atom used to be.
It is like a ghost. It's like a ghost haunting the empty spot on the jungle gym. Just this raw, isolated electron floating in the void, held in place by the positive pull of the neighboring sodium atoms.
I love that visual. And that trapped electron is the star of the show. In solid-state physics, we call this specific type of defect an electron trapped in an anionic vacancy, an F center.
An F center.
Yes, the F comes from the German word Farbzentrum, which translates literally to color center.
A color center. Wow. So this isolated ghost electron is directly responsible for the color change. We go from clear salt to yellow salt because of this one trapped particle. I mean, I understand the geography of it now, like where it is and why it's there.
Yeah.
But the actual mechanism is still muddy to me.
Huh.
How does a single trapped electron interact with light to change what my eyes actually see?
Okay, to answer that, we have to take a slight detour. We need to talk about why things are transparent in the first place. Why does light pass through clear glass or clear water or a perfect salt crystal?
Right, why don't we see them?
We need to introduce a foundational concept in physics called the band gap.
Oh, I've heard the term forbidden zone used for this.
Yeah.
Let me try to visualize this and you tell me where my mental model breaks down.
Go for it.
I'm picturing the electrons inside a perfect salt crystal as being locked into very specific floors of a high-rise building. Like, these are their energy levels. They're all clustered on the ground floor, tightly bound to their atoms.
Okay, yeah.
And for an electron to do anything interesting or to move freely, it needs to absorb energy and jump up to a higher floor.
That is a very functional starting model. In quantum mechanics, electrons can only exist in highly specific, discrete energy states. They literally cannot exist in the space between those states.
Which is so weird to think about.
It is. Your floors represent the allowable energy bands. The ground floor, where the electrons are tightly bound, is called the valence band. The higher floor, where they could theoretically move around freely, is called the conduction band.
And the space between those two floors, the space where no electron is allowed to exist, is the band gap, the forbidden zone.
Yes. Now, light is a form of electromagnetic energy delivered in little packets called photons. When visible light shines on the perfect salt crystal, those photons penetrate the lattice and interact with the electrons on the ground floor.
Like little deliveries of energy.
Exactly. The photons are essentially offering their energy to the electrons, saying, here, take this energy and jump to the next floor.
But the electrons in a perfect salt crystal don't take the offer.
They cannot take the offer. In a perfect, pure salt crystal, the distance between the valence band and the conduction band, the size of that band gap, is incredibly large. It requires a massive amount of energy to cross. And the energy contained in visible light, the light our eyes can see, is simply too weak. A photon of red or blue light doesn't pack enough of a punch to boost an electron all the way across that massive canyon.
So the visible light tries to interact, realizes it doesn't have the requisite energy to force the electrons to make the jump, and it just ignores them.
Because the energy of the photon doesn't match an allowable jump for the electron, the photon cannot be absorbed. The laws of quantum mechanics forbid it. So the photon just continues on its path.
It just phases right through.
It passes right through the crystal lattice completely undisturbed. And when all the wavelengths of visible light pass straight through an object and hit the retina of your eye, your brain registers that material as transparent.
Oh, wow.
That is why perfect salt is clear. The visible light has no available mechanisms to interact with the crystal structure.
Okay, that makes total sense. The gap is too wide, the light doesn't have the juice to trigger a jump, so the light passes through. You see a clear crystal.
Right.
Now, bring back our F center, our trapped ghost electron sitting in the vacancy. How does a single missing atom and a stranded electron change the rules of quantum mechanics for that whole crystal?
Well, it doesn't change the rules for the whole crystal, but it drastically changes the local energy landscape right at that specific spot.
Just around the ghost.
Exactly. When an electron is trapped in that empty physical space, surrounded by positive sodium ions, it forms a completely new localized energy state. In the context of your building analogy, the defect essentially constructs a brand new tiny little stepping stone right smack in the middle of the empty space between the floors.
Oh, like right in the middle of the forbidden zone.
Yes.
It builds a mezzanine level.
A localized mezzanine level, yes. An energy state that absolutely should not and does not exist in a perfect crystal lattice, but is forced into existence by the geometric and electrical reality of the defect.
And this new stepping stone changes the interaction with light entirely. Because now the energy jump required isn't the massive, impossible leap from the ground floor to the top floor.
Precisely. The required jump is just from the ground floor up to this new mezzanine level. Or actually, it is the trapped electron itself sitting in that new defect state that does the jumping.
Oh, I see.
It can absorb energy to jump to a slightly higher excited state within that localized trap. The crucial part is that the energy difference between its resting state in the vacancy and its excited state is much, much smaller than the massive band gap of the overall crystal.
And because the jump is smaller, it requires less energy. Energy that visible light actually possesses.
Yes. The gap is now small enough that a photon of visible light has the perfect amount of energy to trigger the jump.
Okay, let me make sure I'm synthesizing this correctly for the listener. White light, like sunlight, contains all the colors of the rainbow mixed together. And different colors correspond to different energies. Blue light has higher energy, red light has lower energy. When that white light hits our defective salt crystal, the photons encounter this trapped electron.
They do.
And the electron looks at the incoming menu of light and realizes that the energy of, say, the blue photons perfectly matches the exact amount of energy it needs to jump up its new, smaller stepping stone.
It is a resonance phenomenon. The electron selectively absorbs the specific wavelengths of light that match its required energy transition. In the case of the F center in sodium chloride, the trapped electron tends to absorb photons in the blue-violet end of the visible spectrum.
So the blue light gets consumed by the electron to fuel its jump.
It is absorbed, its energy is transferred to the electron. And what happens to the rest of the light? The red, the green, the yellow?
Their energies don't match the jump, so they are ignored. They pass straight through the crystal, just like before, and they hit my eye.
The light that isn't absorbed passes through. And because the blue wavelengths have been subtracted from the original white light, the mixture that reaches your retina is altered.
It's missing a piece.
Exactly. Your brain interprets that remaining mixture heavy on the reds, yellows, and greens as a vibrant yellow. The defect literally carves a highly specific slice out of the visible spectrum, and the absence of that slice is what we perceive as color.
I find that deeply poetic. The color we see is not a physical substance we added. It's the visual echo of a missing piece. It's the shadow cast by an absent atom.
It really is a profound realization when you first encounter it, and it's not just a quirky parlor trick confined to a high school chemistry experiment with table salt. No, this mechanism, or variations of it involving impurities and localized energy states within the band gap, is responsible for the aesthetics of a massive portion of the physical world. Consider the ruby.
The classic burning red gemstone.
Right. A ruby is made of a base mineral called corundum, which chemically is just aluminum oxide. In its perfect, idealized, structurally pure state, an aluminum oxide crystal is exactly like our perfect salt crystal.
It possesses a massive band gap.
Yes, it is completely 100% colorless and transparent to visible light.
Wait, so a flawless, theoretically perfect ruby isn't red at all. It's just a chunk of clear rock.
It would look essentially identical to a piece of sapphire glass. But nature, thankfully, is a messy laboratory.
Messy is good.
Messy gives us rubies. In the chaotic, high-pressure, high-temperature environment deep underground where rubies form over millennia, tiny impurities inevitably sneak into the lattice. Specifically, a few stray chromium atoms manage to squeeze their way into the growing crystal, taking the place where aluminum atoms are supposed to go.
So instead of a vacancy, a missing atom, we have a swapped atom, a substitution defect.
Yes, a point defect, but a chemical impurity rather than an empty space. But the physical result is remarkably similar. Those foreign chromium atoms disrupt the local energy landscape.
Just like the ghost electron.
Exactly. They introduce their own localized energy states, new stepping stones, right into the middle of the aluminum oxide's massive forbidden zone.
Let me guess. Those specific chromium stepping stones happen to require an energy jump that perfectly matches the green and blue wavelengths of visible light.
They do. The chromium impurities absorb the green and blue light to excite their own electrons. The only light that isn't absorbed, the light that is allowed to pass through the crystal and reach our eyes, is the brilliant burning red.
That is incredible. What about a sapphire? They're the same family of gems, right?
They're the exact same base material, clear aluminum oxide. The only difference is the specific type of mistake.
Okay, so what's the mistake in a sapphire?
Instead of chromium sneaking into the lattice, a sapphire formed in an environment where trace amounts of titanium and iron atoms substituted for the aluminum.
And those different elements have different atomic structures, so they create slightly different stepping stones in band gap.
You've got it. They absorb the red and yellow wavelengths, leaving behind that deep oceanic blue.
I mean, every time someone looks at a piece of high-end jewelry, every time we admire the deep hues of a colored gemstone, we are quite literally admiring a beautifully arranged collection of atomic scratches, impurities, and structural mistakes.
It's true.
If the geological processes of the universe operated with absolute perfection, a high-end jewelry store would be visually indistinguishable from a window glass factory.
The aesthetic beauty of the solid world is intrinsically derived from its structural imperfections. Without the flaws to carve up the visible spectrum, our environment would be overwhelmingly drab and transparent.
That perfectly covers the magic of light and how point defects control what we see. But I want to transition to the second part of the claim we made at the beginning.
The magic of electricity and computation.
Exactly. If defects give us color, how do they control the technology we use to run the modern world? Like, how does a mistake make a computer think?
To unpack that, we have to shift our focus from minerals to the undisputed bedrock of the digital age: silicon.
Silicon. We've all heard the word Silicon Valley, silicon chips. It's practically synonymous with computing. And the text mentions that the modern silicon we use to manufacture computer processors is unbelievably pure.
It is arguably the most perfect material humanity has ever managed to manufacture on an industrial scale. The industry standard for semiconductor-grade silicon is what we refer to as 11 nines purity.
11 nines. That means the crystal lattice is 99.9999999% pure silicon atoms.
Yes.
I need to pause and emphasize that scale for the listener, because numbers like that can just wash over you. 11 nines. That means if you have a chunk of this material containing 100 billion atoms, exactly one single atom in that massive crowd will be something other than silicon.
It is a level of structural perfection that borders on the terrifying. It represents decades of intense metallurgical and chemical engineering.
Okay.
But here is the profound irony that material scientists discovered when trying to harness this material. If you take that block of ultra-pure 11 nines perfect silicon and you attempt to use it to build a computer circuit,
It fails.
it will fail completely.
Why? If it's perfect, shouldn't it be the ultimate conductor of information?
No, because perfect silicon, much like our perfect salt crystal, is essentially an insulator at room temperature. It barely conducts electricity at all.
Wait, the fundamental building block of all modern electronics naturally resists electricity. That seems entirely counterintuitive.
It does until you look at the architecture of the bonds. Let's go back to our visualization of the atomic grid.
The jungle gym.
Right. A silicon atom has 4 outer electrons. We call these valence electrons. You can think of them as 4 arms reaching out. Every silicon atom wants to hold hands with 4 other silicon atoms in order to reach a stable, low-energy state.
So they link up. They form a massive, continuous, three-dimensional grid where every single atom is firmly holding 4 of their hands, like a completely locked-in, rigid network.
That is called a covalent bond network. And because every single electron, every single hand is tightly committed to holding onto a neighboring atom, there are no loose hands. There are no free electrons available to detach and move around the lattice.
And electricity, at its most fundamental level, is simply the movement of electrons.
Electricity is the directed flow of charge carriers. If all the available electrons are permanently locked into structural bonds holding the crystal together, nothing can flow.
It's just a traffic jam.
Worse than a traffic jam. It's parked cars with no drivers. If you apply a voltage across a perfect silicon crystal, the electrons just sit there, locked in their pairs. The perfect crystal is electrically inert. It is dead.
Okay, so we have spent billions of dollars figuring out how to make the most perfect electrically dead rock in human history. How do we bring it to life? How do we turn it into a supercomputer?
By intentionally, meticulously ruining the very perfection we just worked so hard to achieve.
Ruining it.
The text describes an industrial process called doping, and it involves an impurity ratio that the text literally refers to as madness-inducing. Scientists take that perfect silicon lattice and they intentionally contaminate it.
How much contamination?
They force in exactly 1 different type of atom for roughly every 1 million pure silicon atoms.
1 in a million. That is the recipe for the digital age. Let me try an analogy to wrap my head around this scale.
Let's hear it.
Imagine a perfectly choreographed stadium event. You have a massive stadium with exactly 1 million people standing on the field. Every single person is wearing a blue hat, and they are all locked, arm in arm, standing perfectly still.
Okay, that is our block of pure dead silicon. The electrons are locked up.
Right. Now, doping it means you walk into that massive locked-in stadium, you find exactly 1 person, and you swap their blue hat for a red hat. And somehow, changing that single hat changes the dynamic behavior of the entire million-person crowd.
The analogy captures the staggering scale of the ratio, but we need to push the mechanics of it a bit further to understand how it changes the behavior. It is not just a cosmetic change like swapping a hat.
Okay, what are we swapping?
You are swapping the fundamental bonding nature of that specific coordinate in the lattice. There are 2 primary varieties of doping discussed in the text, and they form the yin and yang of all modern electronics.
Let's walk through them. What is the first variety?
The first creates what is called an N-type semiconductor. The N stands for negative. To manufacture this, we take our perfect silicon crystal, where every atom has 4 arms, and we forcibly introduce an atom of an element like phosphorus into the grid.
So we substitute a silicon atom for a phosphorus atom.
Exactly.
Okay, phosphorus. How many arms does phosphorus have?
Phosphorus sits right next to silicon on the periodic table, but it has 5 valence electrons. It has 5 arms.
I see the geometric problem already. We are shoving a 5-armed person into a stadium seating arrangement exclusively designed for 4-armed people.
Yes. The phosphorus atom integrates into the lattice. It desperately wants to fit in, so it uses 4 of its arms to lock hands with the 4 immediately surrounding silicon atoms. It forms those 4 covalent bonds perfectly.
But it has a 5th arm left over.
But it has a 5th valence electron that has no partner. There is no neighboring silicon hand reaching out for it. It cannot form a tight structural bond.
Wow.
And because it is not locked into the rigid architecture of the crystal, it remains incredibly loosely attached to its parent phosphorus atom.
Becomes a free electron.
We call it a free carrier. Because it is so loosely bound, it requires an infinitesimally small amount of energy to detach completely and begin wandering through the crystal lattice.
And what does that look like in terms of the band gap we talked about earlier, the forbidden zone between the ground floor and the top floor?
This is where the physics gets beautiful. The presence of that phosphorus impurity with its loosely attached fifth electron creates a new localized energy level. But unlike the F center in the salt, which created a stepping stone right in the middle of the gap,
A mezzanine.
right, the mezzanine, this phosphorus impurity creates a tiny new stepping stone right near the very top of the forbidden zone. It sits just a hair's breadth below the conduction band. We call it a donor level.
Because it's donating an electron to the system.
Yes. And because the stepping stone is sitting right at the ceiling, just below the floor where electrons can move freely, it takes almost zero energy to push that fifth electron up into the conduction band.
How much energy are we talking about?
Yeah.
Do you need to blast it with X-rays again, like the salt?
No. The ambient thermal energy of a room, the basic heat of room temperature, is more than enough.
Just sitting in a room is enough.
That's all it takes. At room temperature, the thermal vibrations simply shake that dangling fifth electron off the phosphorus atom, bumping it up that tiny remaining distance into the conduction band, where it is free to zip through the entire crystal lattice.
So by strategically introducing just one 5-armed impurity per million normal silicon atoms, you suddenly populate the material with millions of free-flowing electrons that are ready to carry an electrical current the moment the chip reaches room temperature.
Exactly. You have created an N-type semiconductor, a material teeming with negative charge carriers.
That is the first half of the equation. Now we must look at the second variety, which is conceptually a bit more difficult to grasp, but absolutely essential.
Yes, this creates a P-type semiconductor. The P stands for positive. For this, instead of using phosphorus, engineers use an element like boron.
I am going to assume boron does not have 5 arms.
Boron has only 3 valence electrons. It has 3 arms.
So we go back to our perfectly packed stadium where everyone is holding 4 hands. We yank one silicon atom out, and we shove boron into that spot. Boron reaches out and grabs 3 neighboring silicon hands perfectly. But there is a 4th neighboring silicon atom, just reaching its hand out into empty space, finding nothing to grab.
Yes. There is a missing electron in the bond network. There is an empty seat at the table. Material scientists refer to this specific type of empty structural seat as a hole, a positive hole.
This is where I always get tripped up. A positive hole. How can an empty space, a literal absence of a thing, carry a positive charge? It's nothing.
It is a counterintuitive concept, but it is physically rigorous. Let's use an analogy. Have you ever played with one of those sliding tile puzzles? The little plastic grids with the numbers 1 through 15 and one single empty square.
Oh yeah, the ones where you have to slide the tiles around to put the numbers in numerical order. I used to play with those all the time.
Right. Think of the solid plastic tiles as our bound electrons and the single empty square as our hole. Now, imagine you want to move the empty square from the right side of the board to the left side. How do you do it?
You don't actually move the empty square itself. You take the plastic tile on its left and slide it into the empty space, which means the empty space has now technically moved one spot to the right.
That is exactly what happens in the atomic lattice of a P-type semiconductor. Nature abhors a vacuum, especially a localized electrical imbalance.
Okay, so the hole wants to be filled.
That empty seat, that broken bond where an electron should be, exerts a strong attractive force on the surrounding bound electrons. Very quickly, a neighboring electron will break its own bond and jump over to fill the empty boron seat.
But by doing that, the electron just created a brand new empty seat in the spot it just left.
Yes. And then another neighboring electron will jump in to fill that new empty seat, leaving yet another empty seat behind it.
So the empty seat is migrating through the crystal.
The physical reality is that billions of negatively charged electrons are taking tiny steps in one direction, but macroscopically, the overall effect is that the absence of an electron appears to be moving continuously in the opposite direction.
I see.
And because an electron has a negative charge, an area missing an electron has a relative localized positive charge.
So as the hole moves, it acts exactly like a positively charged particle moving through the crystal, even though it's technically just a moving void.
In solid-state physics, we treat it mathematically and functionally as a real particle. We call it a hole carrier. It even has a calculable effective mass.
That's wild.
And just like the boron creates this hole, In terms of our band gap model, it creates a new stepping stone right near the bottom of the gap, an acceptor level.
Near the ground floor this time.
Yes, it sits just above the ground floor, making it incredibly easy for ground floor electrons to jump up just a tiny bit into the holes, creating that continuous cascade of movement.
Okay, I think I have the mechanics down. We have N-type silicon, which is doped to have extra free-flowing negative electrons. And we have P-type silicon, which is doped to have migrating positive holes.
Correct.
But I have to ask the ultimate so what question here. If we just want electricity to flow, why do we need both? Why not just use a copper wire or just a piece of N-type silicon?
Because if you just have a piece of copper or a uniform block of N-type silicon, you just have a conductor. Electricity flows continuously as long as voltage is applied.
A bit bad.
You cannot easily control it, you can't make decisions with it. The true magic of the digital age, the invention that literally changed human history, occurs when you take a piece of P-type silicon and a piece of N-type silicon and you fuse them together.
You stick them back to back.
Yes. You create what is called a PN junction. And the physics that occur right at the microscopic border where those two materials touch is what makes all modern computing possible. Let's walk through what happens at that border.
Let's do it. So I'm picturing a block. The left side is N-type, swarming with loose negative electrons. The right side is P-type, swarming with those moving positive holes. We push them together. What happens at the seam?
The moment they touch, chaos ensues at the border. It's a process driven by diffusion. The free electrons on the N side are bouncing around randomly. Some of them wander right up to the border. They look across the boundary into the P side, and what do they see?
They see a massive stadium full of empty seats, the holes.
And electrons naturally seek out lower energy states, which those holes provide. So massive numbers of electrons from the N side immediately rush across the border and plunge into the holes on the P side. They recombine, they fill the empty seats.
Okay, so the electrons cross the border and settle down on the P side. That seems straightforward enough.
But consider the electrical consequences of that migration. The N side was originally electrically neutral as a whole system. The extra electrons were balanced by the extra protons in the phosphorus nuclei.
Right.
But now it has permanently lost a huge chunk of its negative electrons to the other side.
Which means the border region of the N side suddenly becomes positively charged.
Yeah.
It lost its negativity.
Yes, it becomes a layer of exposed positive ions. Now look at the P side. It was also originally neutral, but it just absorbed a massive wave of negative electrons coming across the border.
So the border region of the P side suddenly becomes intensely negatively charged.
You have just described the formation of the depletion region. Right down the middle of the silicon block where the two sides meet, a permanent built-in electric field establishes itself. You have a wall of positive charge facing a wall of negative charge, and this field acts as a massive barrier.
A barrier to what?
To further movement. Once that wall of charge is established, if another free electron from the N side tries to wander over to the P side, it hits that wall of negative charge built up on the P side border.
And since like charges repel.
The electron gets violently shoved back to its own side. The initial migration literally builds a physical force field that stops any more electricity from flowing. The junction naturally turns itself off.
So we built a wall. A microscopic dam blocking the flow of electricity. How is that useful? I thought the point of a computer was to move electricity.
The point of a computer is to control the flow of electricity, to turn it on and off on command. Because we have this built-in wall, we can manipulate it using an external battery or voltage.
Oh, I see.
If we attach a battery to this block in one direction, connecting the positive terminal to the P side and the negative to the N side, we are pushing more holes and more electrons toward the center border.
You're pushing the crowds against the wall.
We push them so hard that they overcome the built-in barrier, the wall collapses, the depletion region shrinks to zero, and a massive surge of electricity flows freely through the entire block. We call this forward bias. The switch is on.
And if we reverse the battery, positive to the N side, negative to the P side.
Then we are actively pulling the electrons in the holes away from the center border back toward the outer edges of the block. We are physically widening the depletion region.
The wall gets thicker.
The wall gets thicker and thicker. The barrier becomes insurmountable. No electricity can flow whatsoever. We call this reverse bias. The switch is off then.
So by applying a tiny voltage, we can collapse the wall or build it up. We can instantly switch the material from a perfect conductor to a perfect insulator, back and forth, billions of times a second.
You have just deduced the mechanics of the transistor. That PN junction, that highly engineered border between two specific types of calculated microscopic flaws, is the fundamental building block of all logic gates, all memory storage, all microprocessors.
Let me sit with that for a second. The smartphone you are holding, the laptop on your desk, the central processing unit inside it contains literally billions of these microscopic PN junctions.
Billions.
Billions of transistors packed onto a piece of silicon the size of a fingernail. And every single one of them, every TikTok video you watch, every email you send, only functions because engineers figured out how to intentionally contaminate perfect silicon with a 1 in a million ratio of trash atoms to create these microscopic, controllable walls of energy.
Without that precise calculated impurity, without the willingness to shatter the perfection of the crystal lattice, the entire digital age simply does not exist. If we demanded perfect materials, we would still be doing complex calculations with mechanical gears and abacuses.
The precision required is just staggering. We are talking about controlling the geographic location and the bonding structure of individual atomic impurities within a matrix of billions of atoms.
That is why the manufacturing facilities for these chips cost tens of billions of dollars. They are managing defects at the parts per billion level. The margin for error in placing those calculated errors is essentially zero.
This has been a very triumphant narrative so far. We have point defects like vacancies giving us the F centers and the beautiful colors of gemstones.
True.
We have point defects like chemical impurities giving us the PN junction and the computer chip. These single atom mistakes seem like the undisputed heroes of the story. But surely not all defects are beneficial. If I crack my phone screen, that's a defect and it definitely doesn't help the phone work better.
You are absolutely correct to introduce some skepticism. Now we must pivot and introduce the primary antagonist of our story.
Okay, the villain.
If point defects, the missing or swapped individual atoms, are the heroes, the text spends a great deal of time outlining a type of defect that is almost universally the villain of the solid-state world. The line defect, which is formally known as a dislocation.
A line defect. So we're scaling up. We are no longer talking about one single atom missing from the corner, but an entire line or plane of atoms being out of place.
Imagine the geometric grid again. If point defects are like missing a single thread in a large woven sweater, a line defect is like grabbing the fabric and pulling it so that a massive puckered wrinkle runs right across the entire chest of the sweater.
Oh, that sounds bad.
You have planes of atoms that are shoved completely out of alignment, creating a continuous linear boundary of intense distortion and mechanical stress running deep through the crystal.
A microscopic wrinkle in the fabric of the material. That sounds deeply disruptive to the orderly flow of things.
It is severely disruptive. Whether you're trying to design a material to conduct a clean electrical signal or a material meant to emit light, dislocations are generally considered a metallurgical nightmare.
Let's examine the mechanics of why they are so bad. Let's go back to our river of electricity, the electrons flowing through the silicon. If the point defects give us the electrons in the holes to allow the flow, what does this massive wrinkle do when the river hits it?
Imagine that smooth, flowing river of electrons traveling through the conduction band. A line defect is the equivalent of suddenly dropping a jagged, chaotic cliff face and a pile of boulders right into the middle of the river channel.
The electrons crash into it.
They scatter violently. As an electron approaches the intense, localized stress field of the dislocation, its path is deflected. It crashes into the distorted lattice structure.
And what happens when they crash?
This scattering drastically slows down the electrical signal, creating massive electrical resistance. But more importantly, when electrons crash and decelerate, they have to shed their kinetic energy.
Energy cannot be created or destroyed, only transferred. Where does the kinetic energy of a crashing electron go?
It is transferred directly into the lattice itself as vibrational energy. In physics, we call these quantized vibrations phonons. But for our purposes, macroscopically, those vibrations manifest as heat.
Oh, heat.
Yes. If a computer chip has too many line defects, the sheer volume of electrons crashing into atomic wrinkles generates so much friction and heat that the chip will literally melt its own circuitry and destroy itself.
So for high-performance electronics, line defects are the mortal enemy. What about for optics? What about the materials we use to create screens or lasers or light-emitting diodes, LEDs?
In the world of optoelectronics, line defects are not just an enemy. Material scientists have a highly specific, very dramatic term for them. They are formally referred to as killer defects.
Killer defects? That implies they are actively destroying the function of the device. How does an LED work in the first place, and how does a wrinkle kill it?
The mechanism of an LED is actually a beautiful application of the PN junction we just discussed. In an LED, we use a forward bias voltage to push the free electrons from the N side and the positive holes from the P side into a central active region.
Pushing them together.
Right. When an energetic electron drops down across the band gap to fill one of those lower energy holes, it releases its excess energy.
Like dropping a bowling ball off a high shelf. And when it hits the floor, the lost potential energy is released.
Yes. And in a carefully designed semiconductor crystal like gallium arsenide, that released energy is emitted as a beautiful, glowing photon of light.
Oh, so that's where the light comes from.
That process is called radiative recombination. The electron recombined with the hole and it radiated light.
So the goal is to get as many electrons dropping into holes as possible, generating a flood of photons. Where does the killer defect come in?
Think of the line defect as a massive, gaping sinkhole in the floor of our building. The core of a dislocation is a region of severe structural chaos. There are dangling bonds, atoms reaching out with nowhere to connect.
Just a mess of broken connections.
Yes, exactly. This creates a deep, chaotic well of localized energy states right in the middle of the band gap. If a wandering electron gets anywhere near this line defect, it gets sucked into the sinkhole before it ever has a chance to find a proper hole and emit a photon.
It gets trapped in the wrinkle.
Yeah.
And what happens to its energy? Does it still flash light?
No. Once it is trapped in the chaotic environment of the dislocation core, it thrashes around, dropping down through a ladder of tiny localized energy steps. It bleeds off all of its energy as a rapid sequence of those phonon vibrations we mentioned earlier.
So it just vibrates.
It loses everything as low-grade, useless heat.
It just vibrates the lattice instead of glowing.
The technical term is non-radiative recombination. The electron fell into the hole, but it didn't radiate any light. The energy was just swallowed by the structural defect and lost forever to entropy.
Wow.
If your LED crystal has a high density of line defects, it will not shine. It will just sit there, consume electricity, get physically hot, and remain totally dark.
Okay, so the rule of the universe seems pretty clear-cut at this point. Point defects, the single atom swaps, are the highly engineered tools we use to build the modern world.
Yes.
And line defects, the massive wrinkles, are the catastrophic failures that destroy our devices and turn our lights into useless heaters. We want the former, we must eradicate the latter.
That was the absolute, unquestioned, unshakable golden rule of solid-state physics for decades. Billions of dollars were spent on manufacturing techniques to grow crystals with zero line defects. Until the early 1990s. Until a researcher in Japan named Shuji Nakamura achieved a historical miracle that completely broke the brains of the scientific community.
This is the story of the blue LED.
The invention of the high-brightness blue LED. It was considered the holy grail, the insurmountable wall of 20th century optoelectronics.
I remember reading a bit about this history. In the 70s and 80s, we had red LEDs everywhere on digital clocks, stereos, VCRs, and eventually we got green LEDs. But creating a blue LED was considered practically impossible. Why was blue so much harder than red?
It comes back to the band gap. Blue light has a much shorter wavelength and a much higher energy than red light. To emit a blue photon, an electron must drop across a very large, very wide band gap.
A bigger jump.
A huge jump. And finding a semiconductor material that naturally possessed a gap that wide, while still being able to be doped N-type and P-type to create the junction, was incredibly difficult. The primary candidate material that physicists identified was a crystal called gallium nitride, or GaN.
So the theory was there. The math pointed to gallium nitride. Why didn't they just grow gallium nitride crystals and make the blue lights?
Because gallium nitride is notoriously aggressively hostile to being grown as a perfect crystal film. It is a metallurgical nightmare.
What happens when they try?
When scientists tried to grow thin films of GaN on a sapphire substrate, the differing atomic spacing between the sapphire and the gallium nitride caused immense structural stress. The growing crystal would inevitably tear itself apart at the microscopic level.
Oh no.
Every single time they grew it, it was completely riddled with line defects.
The killer defects, the wrinkles, the sinkholes.
By the millions. The accepted scientific wisdom of the era was mathematically strict. If a semiconductor crystal had a dislocation density higher than, say, a few thousand defects per square centimeter, it was garbage.
Because of the non-radiative recombination?
Exactly. It would completely dominate the material. It would never emit usable light. Most major research institutions abandoned gallium nitride entirely because it was deemed impossible to grow it clean enough.
But Nakamura didn't abandon it. He pushed through and eventually built a working diode out of this material. What was the quality of his gallium nitride crystal? Did he somehow invent a way to grow it perfectly without any line defects?
He did improve the growth method significantly, but the resulting crystal was nowhere near perfect. The text we are reviewing provides a truly mind-bending comparison.
What does it compare it to?
It notes that the density of the line defects in his successful material was comparable to the heavy, thick treads on a mountain bike tire.
I'm trying to visualize that at an atomic scale.
His crystal did not have thousands of defects. It had hundreds of millions, perhaps billions of line defects per square centimeter.
Billions.
The atomic structure was completely lacerated with killer defects. It was the microscopic equivalent of a shredded, puckered rag.
Based on the physics we just spent 20 minutes discussing, that material should have been completely dark. Any electron injected into that lattice should have instantly fallen into a killer defect, vibrated the crystal, and died as heat.
By every known law and heuristic of solid-state physics at the time, his device should have been a complete catastrophic failure, a useless hot rock.
But it wasn't.
No. Here is the historical anomaly that eventually won Nakamura the Nobel Prize in Physics. When he finally fabricated his p-n junction and hooked his shredded, defect-riddled gallium nitride crystal to a battery, it didn't just produce a faint glow, it shined with piercing, ultra-high efficiency, brilliant blue light.
How is that physically possible? That seems to violate the very mechanics of the sinkhole effect you just described. Why didn't the electrons get sucked into the wrinkles?
That is the exact question that paralyzed the physics community when the discovery was published. It took years of intense microscopic analysis for physicists to fully understand the mechanism of why it worked.
And what did they find?
The answer is one of the most elegant paradoxes in material science.
Okay, walk me through it. How did the worst material ever made produce the brightest light?
It turned out that the specific chemical nature of the alloy Nakamura used specifically adding indium to create indium gallium nitride in the active light-emitting layer created a secondary effect that neutralized the killer defects.
Indium. Okay, what does indium do?
When you mix indium into the lattice, the indium atoms, which are slightly larger, don't distribute perfectly evenly. They tend to cluster together in microscopic patches due to internal strain.
So we have clusters of impurity atoms scattered throughout the shredded lattice.
Yes, and these specific clusters of indium cause localized dips in the band gap energy. They create tiny, microscopic, three-dimensional valleys of low energy. The literature refers to these as compositional fluctuations, or more simply, quantum pools.
Quantum pools.
Yeah.
Like little localized puddles of low energy scattered across the floor.
Think of it as a landscape. You have a floor full of massive, fatal sinkholes, the line defects. But you also have millions of these shallow, gentle quantum puddles scattered everywhere between the sinkholes.
Okay, I picture it.
When the electrons in the holes are injected into this chaotic crystal, they begin wandering across the landscape.
Heading toward the sinkholes.
But before they can reach the killer dislocations, they inevitably stumble into one of these shallow quantum puddles. And once an electron falls into a puddle, it becomes highly localized. It gets physically trapped in that tiny spatial region.
All right.
It literally cannot migrate any further across the crystal to reach the sinkhole.
It is corralled. It is trapped in a safe zone.
The quantum pools act as protective barriers. The electrons and the holes both get trapped in the same puddles, and because they are forced into close proximity within a safe, low-energy environment, they have no choice but to undergo radiative recombination right there on the spot.
So they emit light.
They drop across the gap and emit brilliant blue light before they ever encounter the killer defects.
That is an unbelievable mechanism. The material is essentially saving itself from its own fatal flaws by using a different set of flaws, the clustered impurities, to trap the energy.
It is a breathtaking synergy of defects. It proved a profound, paradigm-shifting point to the scientific establishment.
It was.
Sometimes, even the absolute worst, most destructive structural defects can be incorporated into a miraculous, world-changing material, provided that the overall architecture of the system is manipulated and understood correctly.
You don't just throw it away.
You do not always need to eradicate the flaws to achieve brilliance. Sometimes you just need to design a complex internal environment where the fatal flaws are naturally neutralized, bypassed, or outmaneuvered by the system's own geometry.
This entire journey we've taken today is really forcing a massive paradigm shift in how I visualize the physical world around me. We have gone from the colorful kitchen salt on a dining table to the billion transistor silicon chips running the servers of the internet to the blue light emitting from the screens we stare at all day.
And they all share a common theme.
Right. The common denominator through all of it is that absolutely none of it is perfect.
That is the core synthesis of our deep dive today, and the primary thesis of the text we explored. The history of materials science, which is functionally the history of the modern technological revolution, is emphatically not a history of striving for geometric perfection.
Is the exact opposite. It's a history of learning how to creatively break things.
It is a history of hacking the nanoworld. We have this popular cultural image of semiconductor engineers and physicists. We picture them in pristine, pressurized clean rooms, wearing full-body white suits, looking through multi-million-dollar transmission electron microscopes with bloodshot eyes.
Measuring impurities down to parts per billion.
Exactly, and as laypeople, we naturally assume they are doing that to make sure the material is flawlessly clean. We think they're trying to eradicate every last speck of dust, every rogue atom, to achieve some platonic ideal of a crystal.
But they aren't.
But they aren't. They are obsessing over the parts per billion because they are meticulously, surgically inserting and managing the flaws. They are hacking the crystal lattice. They are architects of imperfection.
To summarize the elegant triad of phenomena we have explored today from the source text, we learned first that vacancies, the missing atoms, the empty physical holes in the lattice, can trap rogue electrons to act as tiny localized catcher's mitts for photons, carving up the visible spectrum and giving a transparent, colorless world its vibrant, breathtaking color.
The aesthetic beauty of the void.
Yes. Second, we learned that impurities, the swapped atoms that calculated 1 in a million additions of elements like phosphorus or boron, provide the free electrons and the migrating positive holes.
The charge carriers.
Exactly. They provide the necessary charge carriers that give dead, insulating rock the breath of life, allowing electricity to flow, be controlled at a p-n junction, and power the logic gates of the digital brain.
The foundation of all computation.
And finally, we learned that even the undeniable villains of the micro-world, the dislocations or massive line defects, while acting as chaotic sinkholes that can destroy an electrical signal or kill a photon, can also be navigated.
Right.
By layering defects upon defects, like the quantum pools in the blue LED, scientists can bypass the killer wrinkles entirely, completely redefining what is physically and mathematically possible to manufacture.
The perfection of our daily lives, the smooth, frictionless glass of our interactive screens, the flawless, high-speed execution of our software algorithms, the vibrant, true-to-life colors of our high-definition displays, all of it is a macroscopic illusion.
An illusion built on mistakes.
It is a user interface powered by an army of beautifully engineered imperfections, working tirelessly in the dark at the atomic level.
So, as a final takeaway for you, the listener, the next time you pick up your phone to send a text, or admire the deep hue of a piece of jewelry, or even just look at the salt shaker on your kitchen table, I hope you look at the physical fabric of the world with a little more appreciation and perhaps a little more affection.
I agree completely.
It is not a pristine, untouchable geometry dictated by rigid perfection. It is a messy, scratched, highly negotiated, perfectly flawed masterpiece.
It really is a marvel of calculated chaos.
Well, that officially wraps up our deep dive for today. Thank you so much for joining us on this extensive journey into the atomic wrinkles of the universe. It has been a genuinely perspective-altering conversation.
If I may, I would like to leave our listeners with one final, slightly more philosophical thought to mull over before we sign off.
Oh, absolutely. What is it?
We've spent this entire hour talking deeply about microscopic crystal lattices, solid-state physics, and the hardware of modern technology. But I think the mechanics we've discussed raise a profound, analogous question about how we view the world at large, beyond the confines of the laboratory.
I am intrigued. How so?
Consider the current trajectory of human behavior. We spend an enormous amount of our time, our capital, and our emotional energy trying to engineer perfectly frictionless systems. We demand perfect, predictive algorithms to dictate our social feeds and our entertainment.
We do.
We strive to build flawless, optimized corporate structures and utopian social models. At an individual level, we endlessly optimize our own daily routines, our diets, our productivity, desperately trying to eradicate every error, every inefficiency, every perceived personal flaw.
We are undoubtedly a culture completely obsessed with total optimization and the eradication of friction.
But if the fundamental physics of the universe, the literal mathematical bedrock of reality we just explored, dictates that true power, true color, and monumental technological progress can only ever emerge from precisely engineered friction, from flaws and mistakes interacting in complex ways, What essential, beautiful defects are we accidentally trying to erase from our own human systems right now? If we successfully engineer all the friction and flaws out of our lives, do we just end up like the perfect salt crystal?
Transparent, uninteresting, and fundamentally dead. That is an incredibly powerful thought to chew on. Let the flaws do their work.
Yeah.
Until next time.